Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iman bin Rosli, and my group is will be presenting about a research paper with the title of An Insight into a Development of Bottom Water Reservoir. So, for the introduction, as you can see in the image, which is a water conning. Water conning usually is a problem in the conventional vertical wells that produce in underwater bottom reservoir condition. So, as the research paper is researching about horizontal well is much popular as it's expected higher productivity and reducing water conning. So water conning can be also reduced by natural barriers like shell sticks. Next one, we will talk about shells. So what the function of the shells is to increase the totality of fluid flow path and thus decrease the effective single-phase permeability of the reservoir. Next one, the shell barriers are divided into two, which is one continuous and the second one is discontinuous. So continuous are the shell barriers with no lateral extent within the formation, while the discontinuous are shells can be correlated between wells and distributed randomly to the porous media. As you can see, the image below shows continuous shells and discontinuous shells. Without further ado, uh, in this research paper, the topics we will discuss is first one is to apply a horizontal well technology with the help of flow barriers in a more systematic way to develop bottom water reservoir. The second one is effective way of production by conducting series of 3D reservoir simulation. So the third one is studying the effects of properties of single horizontal continuous shell on horizontal well performance under bottom water reservoir condition. So next one, finding the effects of shell parameters on water cut, cumulative oil production and cumulative water production, and to compare them to those results in the same formation without the shell body. And the last one, finding the applicability of heavy oil development using horizontal well with the presence of low permeability shell barriers. That's all from me. Thank you.
Hello, my name is Chol Gai Kul Dut. Well, basically, I will be talking about the description of the reservoir and the numerical models. The computer modeling groups called CMG stars advanced process and the thermal reservoir simulator was employed or used as a 3D numerical model for this investigation. And this is actually demonstrated in the picture below. And to reduce water conning and run parallel to the x coordinates, a centrally positioned horizontal well with a length of 570 feet is completely evaporated in the upper second layer, and therefore the shell is considered to be a horizontal well and run along the x coordinates. Well, to continue from the previous slides, the next one is the bottom water, which is molded by a regional aquifer at the bottom of the reservoir. And the basic data used in the simulations are summarized in the graph as shown. And so the Cartesian grid system is selected, and the reservoir is discreted into 17 blocks along the x and y directions, and also 7 blocks along the z directions. So to investigate the effects of a shells on a vertical water conings, the blocks near the shells are split into a refined grid blocks in the z directions. And because the main goal of this studies is to establish a compressive trends in the performance of the horizontal wells in both homogeneous and octogenous performance, the grid blocks are kept constant throughout the analysis in order to minimize the undesired grid effects. And so to comply to the reservoir grid systems, the single and continuous shell barrier is considered to be a planar and parallel rectangular objects for the reservoir modeling purpose. Next is the numerical simulations. So after creating a 3D simulation models, the following specific parameters are evaluated or investigated first. So the first one is the shale vertical permeability, and the second one is the shale length, the third one is the shale's width, and the fourth one is the shale vertical operations, and the last one is the shale relative horizontal operations. Well, next, the outcome of various instances compared to the base case in which no shale barrier exists. So in table 2, the list of the parameters chosen in the preceding 5 sections are demonstrated as shown. And secondly, there's implications of shales on the horizontal wells performance for various viscous oils are investigated. And finally, there's a potential of implementation on the grounds in which oil reservoirs with bottom water is carried out, which include the use of broken horizontal wells, the solvents, or a stream injection on the midst scale.
Hello, my name is Isaac Ajang, and I'll be taking part in the results and discussion. So we shall look at the result of the effect of shale vertical position. So here the vertical distance from the water or oil contact to the shale barrier is used to define the shale vertical position. Also we can see here the further the shale from the water uh, bottom water zone, we can see also the lower the water cut and also the lower the cumulative water production is going to be. So when the shale barrier is in the aquifer, the relatively poor effect is observed to compare with the cases where the shale is located above the aquifer. So before the water breaks through into the case without the barrier, we can find that the productive index is larger than those in the case with the barrier under the condition of the same liquid production rate. Also, we can see the further the barrier to the horizontal well, also the larger the productive index is, and this is because that there is existence of a barrier which provide the flow resistance. Here we can also see that after the water breakthrough in the case with the barrier, the productive index decrease, and for the cases with the barrier, the horizontal producer can maintain a relatively longer water-free production period, and the productive index decreases gradually after the water breakthrough. It is also known that in the case where the barrier is close to the horizontal well, the productive index curve is always less than those of the other cases. So in the case of the effect of the shell length, we have 5 different shell lengths we examined, as it is mentioned here in the slide. So, so the result is going to be in the comparison of the water cut for the low shell permeability cases and the base cases. So we can see the longer the shell length, we can see that the lower the water cut will be under the condition of the same producing time. And also there is a relatively a larger base area of the water cone to compensate for the resistance to flow, to water flow. Why? Due to the permeability shell and also the feed coin with the same amount of water. And also the low permeability layer can predict to slow down the increase of water cut. To discuss the effect of the shell with 3 different cases were examined, as we see the lens here in the slide. So this result is in comparison to the base, and the wider the shell width, the lower the water cut will be at the same producing time. So in the case of 285 feet and 475 feet, the shell width and the water cut curve are almost similar, which is identical. So this implies that the area of the barrier are large enough to reduce the coning and water production. Also, with the increase in the area of the shale body, uh, which is by increasing either the length or the width, so the effect of the shale body on the well producing will be stable. In this case of effect of shale vertical permeability, 6 cases with a different shale permeability were analyzed, and we can see that the water breakthrough occurs much easier in the base case than in the reservoir, which contains the shale barrier. And also in the base case, the water breakthrough is occurred after 250 days of production. Also, the water cut development in the case of the shale barrier shows that the water breakthrough after 900 days of production, which is also the well in the base case has a water cut of only 58%, where for the case of shale barrier with the shale permeability of 0.5 millidarcy, um, which is after the same amount of time, the water cut is only going to be 10%. So it is also observed that the cumulative oil production increased significantly and the water production decreased in the situation containing the shale barrier compared to the base case. For the effect of shale horizontal position, three situations here were considered. We can see that the shale right below to the horizontal well, which is equal to 80, can be more efficient base the water production than the other two, which is greater or less than 0. And also we can see that there is a difference between the condition which the shale is close to the hell end of the horizontal. So in this case, the shale position is less than 0, and that is the toe end of the horizontal well. The shale position here is greater than 0. It is also observed that the lowest flowing pressure exists at the hell, and hence the water breakthrough around the hell would be much faster in the former case than the later case. Also, when the shale barrier is not directly placed underneath the horizontal well, the flow direction in the horizontal well is considered to be a better. It has a better performance. So our last result here is on the effects of the oil viscosity. So in this case here, 6 simulation cases were run for the different viscous reservoir oil or without the cell body. So in the case with the oil viscosity of 1000 center point, which is less than 80%, and also in the case with oil viscosity of 1 center point, which is always less than 10%. This is due to water coning tendency is more severe in in heavy oil reservoir, which it is well known that it has a higher water or oil mobility ratio than the lighter oil reservoir. So in the case of the reservoir with a strong bottom water drive, the horizontal well performance is much better in the presence of horizontal shale barrier for high viscosity oil reservoir. So basically, this strategy here of the oil viscosity is very important for only heavy oil development with the active bottom water supports, as we can see here from the figure, which shows the effect of shale on the water cut for different viscous oils. So, ladies and gentlemen, this is the end of my part. Thank you.
Hi, my name is Afiq. I'm going to present about possibility of field implementation in heavy oil reservoir and also the conclusion part. Okay, as we all know, most of the heavy oil reservoir have an active bottom water. This will result in high water oil ratios, but previously it shows that having a flow barrier will delay and suppress water production in the reservoir. So this is the three case study that are made to actually help the engineers to further look into heavy oil horizontal well. So the first one, we have fractured horizontal well, then we have solvent injection assisted process, and lastly we have steam injection process. So from the previous analysis, it shows that fractured horizontal well with barrier will provide increase up to 145% in cumulative oil production, and also decrease water production up to 44%. So this is important as we all know that in oil and gas production, reducing the water production will help to reduce other problems such as corrosion, um, salts deposition, and water disposal. Also, this all will need costs to actually mitigate it. So that is why fractured horizontal well with barrier will actually help with the water problem, as it will delay the water production in the well, which results in higher oil production, increase the time of the oil production without the water, and also less cost issues. Then we have solvent injection assisted process. In this study, two type of solvent are used, which is the methane and propane, and also carbon dioxide solvent. So in the case of carbon dioxide injection, it is observed that it increased 2.2 times higher than the base case, the oil production, and also lower the water production to 1.37 times lower. So this happened through the process of CO2 injection, will that will actually swell the oil, the heavy oil. So the swollen oil droplets will force fluids out of the pores, creating a drainage process. So this process causes the trapped droplets that cannot move under present pressure gradient to move toward production well. And then we have the methane and propane, which is hydrocarbon vapor. So through methane and propane injection, um, the oil production increased 2.72 times higher. This happened through the process of diluting the heavy oil and make it easy to mobilize. So compared with CO2, uh, this mixed solvent injection process, which is methane and propane as well know, can achieve a higher oil recovery even at less injection volume, and also it is less expensive. Lastly, we have steam injection process. The paper that we work on is published in 2004. So in that paper, this is just a theory where no testing have been done. So after further research, there is two type of steam injection, which is in testing phase in heavy oil horizontal well, which is the steam half and puff, which is a cyclic process, and also steam drive. So in steam half and puff, just as the name suggests, the first stage is injection. So during which a slug of steam is introduced into the reservoir. That is the half. So the second stage, or the soak phase, requires that the well to be shut in for several days to allow uniform heat distribution to thin the oil. So finally, the third stage, the thin oil is produced through the same well, which is called the puff. So that is what half and puff is. And we have a steam drive. So steam drive is basically where you inject steam to into the well to heat the heavy oil and reduce the viscosity, so it will be easier for the heavy oil to move to the production well. So this method is best used for the top water reservoir, where there is no active bottom water to provide the drive for the oil. And now to conclude what we have found from the research paper. First, the low permeability shale barrier does delay water breakthrough and can be beneficial for production process. This is helpful as it increases the time for oil production without having to deal with water production in early stages. Secondly, the water breakthrough time and the well performance are not increased monotonically with the decrease of shale permeability. So there exists an optimal shale permeability, meaning there is a sweet spot for the shale permeability and also an optimal shale width and length. It will also help to drill the well, the horizontal well, aligned with the shale orientation to provide the best barrier orientation. Third, position of low permeability barrier must be above all water contact to help mitigate water corning problem with bottom water reservoir. And the barrier must not be too close to the horizontal well. Fourth, the study of different viscous oil shows the horizontal well performance is better in the presence of horizontal shale barrier for heavy oil. So this strategy may be very promising for the heavy oil development reservoir with active bottom water support. Having the barrier naturally will provide more time before the needs to inject barrier to mitigate water production problems. So fifth, if there is no natural barrier, we need to integrate other strategies such as stimulation, small scale CO2, steam, and solvent injection to provide an artificial barrier. So with that, thank you for listening, and we will entertain any question that you guys will ask. Thank you.